Today we will now discuss annihilators. These will play an important role when we study the relationship between the kernel of an operator, the range, the kernel and range of the adjoint of an operator, and so on. So these are important objects. So we have already seen one of them. So we have W contained in V. So V Banach, this we will assume this, since we are going to use open mapping, closed class theorems, etc. We will always work in Banach spaces for the moment. Okay. Then the annihilator W perp is set of all f in V star such that fx is 0 for all x in W. So similarly, if you have Z contained in V star, we can define the annihilator Z perp. I am not going to use the same definition and go to V double star. Instead, this is the dual relationship. So this is set of all x in V such that fx is 0 for all f in Z. So this is a subspace of V star and this is a subspace of V. So I will use the same symbol. I don't want to change the position of the perpendicular symbol. So that, but from the context, depending on where the subspace is living, we will understand where the space is. Okay. So if both W perp is a closed subspace of V star and Z perp is a closed subspace of V. We have already seen the first one in one of the exercises earlier. The second one is absolutely the same. So now let me take W perp perp. So I am going to take W perp is now a subspace of V star. I take its perp. So this is something in V now. So if you take any element x in W, that will be killed. When I say killed, that means the valuation is 0. So that will be killed by every element of W perp, and that means it belongs to W perp perp. So W perp perp contains W. Because if x is in W, then for every element in W perp, f of x will be 0, and therefore x has to be in W perp perp. Since the perpendicular is a closed subspace, so it contains W, so it will also contain the closure. Okay. Now, what about, do we have equality? Yes, we do. So suppose we have a x in W perp perp minus W closure. Then Hahn-Banach tells you there exists a f in V star such that f of x is not 0, but f restricted to W is identically 0. This is one of the corollaries of the Hahn-Banach theorem. Consequently, f belongs to W perp. And since x is in W perp perp, this means that f of x has to be 0, which is a contradiction. And therefore, we have that W perp perp is in fact equal to W closure. Now, in the same way, if you take Z perp perp, that will contain Z closure. But now you try to imitate the same argument, you will fail, because now you have to take, when you apply Hahn-Banach, something in V double star, and that doesn't come in anywhere in our calculations here. So we only can say this much, but equality if V is reflexive. Because now then this, if V is reflexive, V double star is nothing but V, and therefore you can repeat the previous argument, and therefore you have this. Then finally, if G is contained in H, in V, then this implies that H perp is contained in G perp. That's very obvious, because everything which kills, if a continuous linear function kills all of H, then it will kill all of G, and therefore it belongs to G perp. Okay, so now we will prove a proposition. So G and H closed subspaces of V, which is Banach, of course. Then G intersection H is G perp plus H perp perp, and G perp intersection H perp equals G plus H perp. So the second condition thing is almost obvious. Something kills both G and H, it will kill all of G plus H, so it will belong to G plus H perp. If something is in G plus H perp, so in particular it will kill all of G plus H, in particular it will kill all of G, and it will kill all of H, so it is both in G perp intersection H perp. So this one is obvious. So now let us prove the first one. So proof. We already have that G intersection H is contained in G perp plus H perp perp. Why? Because if you have something in G intersection H, then it is killed by everything in G perp, it is killed by everything in H perp, so it is killed by everything in G perp plus H perp, that is, it belongs to G perp plus H perp perp. Okay, now for the converse, we have that G perp is contained in G perp plus H perp, and therefore G perp plus H perp perp is contained in G perp perp, and that is G closure, and G is closed, so that is G. Similarly, H perp is contained in G perp plus H perp, so the same reason G perp plus H perp perp is contained in H perp perp, which is H closure, which is H, and therefore we have the second relation is also true, namely the reverse inclusion, and therefore this is also true. Okay, now you combine these two, we get the following with the preceding observations. So we get the following corollary. G intersection H perp. So if I take the perp of this, it contains G perp plus H perp double perp. So this contains G perp plus H perp double perp, but this is a subspace of V star, so it contains G perp plus H perp closure. And now if I take the second relation, so I get G perp intersection H perp perp, that's equal to G plus H double perp, but that is G plus H closure. So G plus H closure. So these two corollaries, this is just a corollary. Okay, so now another proposition. So V Banach, G and H closed subspaces such that G plus H is also closed. This is a non-trivial thing. This is not obvious. If G and H are closed, G plus H need not be closed. So we are making this observation. Then there exists a constant C such that for every x in G plus H, there exists A in G, B in H with norm A less or equal to C times norm X, norm B less or equal to C times norm X, and X equals A plus B. Okay. So, what does this mean? Given any, if the sum of two closed subspaces is also closed, then you can decompose any vector into a sum of a vector in A and a vector in G and a vector in H, but in a continuous fashion. Okay, so there are many decompositions possible, but you will be able to select one in a manner that is uniformly continuous. Okay, so proof. So you consider the spaces G cross H with the norm. So xy norm, we have already seen this, is in G cross H is norm G, norm X plus norm Y. So given a product, now both are closed subspaces of a Banach space, so each one is a Banach space in its own right. So the product is a Banach space with this as the norm. We have seen the dual of such a space in one of the exercises already. So now G plus H is also closed, so it is also a Banach space. So G plus H closed implies complete. So this is also complete since G and H closed. So we have two complete Banach spaces and we are going to take a mapping from G cross H into G plus H. So we are going to take xy going to x plus y. So this is linear and this is obviously continuous by the definition of the norm. Norm of x plus y is less than equal to norm x plus norm y, which is the norm of x comma y, and therefore this is linear, continuous, and above all it is onto, because every element of G plus H can be written as a sum of 1 in G, 1 in H, and therefore this map is linear, continuous, and onto. So then there exists a C by the open mapping theorem. So this is the open mapping theorem. There exists a C positive such that Z in G plus H, norm Z less than C, that means it belongs to B0 C in G plus H, then that must belong to the image of the unit ball. Okay, so such that implies there exists x in G, y in H, such that Z equals x plus y and norm of x plus norm of y is less than 1. So this is the theorem, namely the balls in G plus H center origin radius C is contained in the image of this map of the unit ball. So that is what we have said. Now if Z is an arbitrary vector, so if Z belongs to G plus H, then you consider Z by norm Z, this is norm 1, and take C by 2, so its norm is of C by 2, which is strictly less than C. So this can be written as x dash plus y dash, okay, and norm of x dash plus norm of y dash will be strictly less than 1, x dash in G, y dash in H. Then you write Z equals x plus y, x in G, y in H, where x equals 2 by C x dash, y equals 2 by C y dash, and therefore sorry, 2 by c norm z, and therefore you have the norm z should come up. Just go back to what we had, the norm z. So 2 by c norm z, that will go to the numerator now, and therefore you have norm x will be less than or equal to 2 by c norm z, and norm y will be less than or equal to 2 by c norm z, and therefore every z, so this is the constant we are talking about, and therefore everything can be uniform. So now let us, a corollary to this thing, let us say G intersection H is singleton 0 and G plus H closed. In particular, let us say G plus H is equal to V. Then you have V equals G direct sum H. But in this case, the decomposition is unique. There is no several decompositions possible. So by the previous theorem, you have that Z in V, then Z has a unique decomposition x plus y, x in G, y in H, uniquely defined, and you will have norm x less than or equal to C times norm Z, norm y will be less than or equal to C times norm Z. And these are precisely the projections from V. So Z going to X and Z going to Y are precisely the projections of V onto G and H respectively. So if you have a decomposition, if G plus H is closed or G plus H is whole of V and G intersection H is singleton 0, then the projection is continuous. That is a consequence of the open mapping theorem. Otherwise, the projection need not be continuous. Okay. So now I will going to state a theorem. G and H closed subspaces of a Banach space V. The following are equivalent. One, G plus H is closed in V. 2, G perp plus H perp is closed in V star. 3, G plus H equals G perp intersection H perp perp, and 4, G perp plus H perp equals G intersection H perp. So these 4 are equivalent. Now we already know that G perp intersection H perp is G plus H perp. So if I took the and then we had the further corollary that G perp intersection H perp perp is G plus H closure. So G perp intersection H perp perp equals G plus H closure. So if G plus H is closed, then this is G plus H and you have this relation, relation 3. Conversely, if you have relation 3, then you have G plus H closure is G plus H and therefore G plus H is closed. So it is obvious that 1 is equivalent to 3. Also 4 implies 2. Why? Because if G perp plus H perp is equal to a perp, perp is always closed and therefore G perp plus H perp must be closed. So 4 implies 2 is also obvious. So to complete the proof, we need to show that 1 implies 4 and 2 implies 1. Because 1 and 3 are equivalent, so 1 implies 4, 4 implies 2 is just done, and therefore 2 implies 1. If you can do all this, then of course this theorem is proved. So let us prove 1 implies 4. So what does 1 say? G plus H is closed. So we already know that, we already proved this in a corollary. G intersection H perp contains G perp plus H perp closure, and that of course contains G perp plus H perp. So we need to prove, to show G intersection H perp is contained in G perp plus H perp. So let F belong to G intersection H perp. So define a linear functional on G plus H as follows. So x belongs to G plus H. So x can be written as A plus B, A in G, B in H. So define phi of x equals f of a. So we have to first check that this is well defined, because what have we done? We have taken a decomposition and then in terms of the decomposition we have defined this functional. So it should be independent of the decomposition chosen, only then this becomes well defined. So if x equals a plus b equals a dash plus b dash, where a dash are in G, b dash are in H. Then what you have, that a minus a dash equals b dash minus b. So this belongs to G, this belongs to H, and so this belongs to G intersection H. But f belongs to G intersection H perp, and therefore f of a minus a dash equal to 0, which implies that f of a equals f of a dash. So whatever may be the decomposition you take, phi x equals f of a, then the answer will always be the same. So therefore this is a well defined linear functional. Also, there exists a C positive and we can choose AB such that norm A is less than or equal to C times norm X, norm B is less than or equal to C times norm X. This is the previous proposition which we already proved based on the open mapping theorem. Therefore, mod phi of a, phi of x, okay, and why is this so? Because since G plus H is closed, that was the proposition we proved, and therefore, so mod phi of x is less than or equal to mod f of a, which is less than or equal to c times norm f times norm a, which is less than or equal to c times norm f norm x, and therefore phi is a continuous linear functional on G plus H. Therefore, by Hahn-Banach, there exists an extension phi tilde from V. Defined on. So phi tilde will be equal to phi on G plus H. Therefore, phi tilde equal to phi on G and phi tilde equal to phi on H independently, and so this is equal to 0 because phi is 0 on H, because any element in H can be written as 0 plus itself, and therefore the f of 0 is 0. So that is the thing. So on H this function phi is just 0. And now if you took f minus phi tilde, they both agree f is the same as phi. F of x equals phi of x equals f of a, and therefore f equals phi on G, and therefore f equals phi tilde on G also. This belongs to G pop. So this implies phi tilde belongs to H pop, and therefore we can write f equals phi tilde f minus phi tilde plus phi tilde, so which belongs to G pop plus H pop. So that completes the proof. Okay, the last inclusion I am not going to do, namely 2 implies 1. This is a bit long and very technical, and there are really no new ideas, but it's somewhat contrived proof. So it is best if you read it yourself. It's in the book, so you can check it out, and otherwise it will take a lot of time to explain, and so we will and since it does not, it's just some technical device, and therefore we will assume this theorem. Okay, so this theorem is more or less proved except for this 2 implies 1, which I am going to omit the proof for lack of time. Okay.